I'm going to start new chapter 10 on the topic wave optics. And in this chapter, you will learn or you will learn in details about the topics wavefront. Before that, electromagnetic waves that has already been discussed in chapter 8. Still, as light itself is an electromagnetic wave, therefore, it is essential to discuss about electromagnetic wave before going deep into the wave optics, because light itself is an electromagnetic wave. So, first of all, let us recap the important terms that we have learned in electromagnetic wave, and then we will correlate these terms with the ongoing topics, optics. And next foremost topic is wavefront, which is new to all of you, because in class 10th you have already studied about the ray optics. But here in this section, we will study the another aspect of light, that is wave optics, and the terms that would help you to explain wave aspect of light, that is wavefront. Okay. And after dealing, हाँ जी, क्या प्रॉब्लम है? Is there any problem? After dealing with the wavefront, then we will be able to discuss a fundamental principle that would prove the optical phenomenon, that like refraction and reflection, law of refraction and law of refraction, and reflection of light based on Huygens principle, refraction of light based on Huygens principle, and behavior of wavefront in mirror, lens and prism, coherent source of light, and then interference, and Young's double slit experiment, and colors in the thin films. And after that, we will discuss in another part of the optics, wave optics, in which we will discuss about polarization and diffraction. So let us start with the first topic, electromagnetic wave. We have already discussed that electromagnetic wave consists of two kinds of field mutually perpendicular to each other and continuously varying in magnitude and as well as in direction periodically. So electromagnetic wave can be represented by a periodic function like sine or cosine function. So variation in both electric and magnetic field occurs simultaneously. Therefore, they attain their maximum and minimum at the same place and at the same time. So you can see that electric field and magnetic field both are coherent in a spatial coherent and temporal coherent. Temporal associated with time and a spatial associated with space, place. Now, the direction of electric and magnetic fields are mutually perpendicular to each other. You know well, in the previous chapter I have already discussed. And as well as these two fields are perpendicular to the direction of propagation of the waves. Third point is that the speed of electromagnetic wave depends entirely on electric and magnetic properties of the material medium. in which the wave travel and not on the amplitude of their vibration. So this is the waves which depends only the property, magnetic and electrical properties of the material medium, not elastic property. And that's why if amplitude decreases, speed remains same, because amplitude on decreasing amplitude, there will be change in wavelengths. And as a result, change in wavelengths, speed will get changed. It is because of this reason when light passes from one medium to another medium, its speed changes because of change in amplitude. And change in amplitude causes change in wavelengths, while frequency will remain same. Now, wave is propagating along x-axis with a speed c equal to 1 over root under mu naught epsilon naught. That has already been discussed in chapter 8, electromagnetic wave. You know well that mu naught is the magnetic permeability and epsilon naught is the electrical permittivity of the vacuum. It means a speed of light depends on magnetic and electrical property of the material or medium in which light is propagating. So as soon as light make a transition from one medium to another medium, everything will remain same, but magnetic properties of the material medium will be different for different material medium. That's why a speed of light will be different for different material medium, because mu and epsilon naught will get changed there, because mu naught and epsilon naught is constant for the vacuum. But as soon as we enter into the another material medium, value of magnetic permeability mu and electrical permittivity epsilon will get changed. Now, for discussion of optical property of electromagnetic wave, more significance is given to the electric field E, not magnetic field, because most of the materials interact with the light in terms of electric field, not in terms of magnetic wave, because you know that material is made up of tiny particles called atom, and atom consists of moving charged particle like electrons, and nucleus of atom consists of positively charged particle confined in the nucleus, and hence this positive charge particle creates a sphere of its own electric field. Therefore, every material medium is associated with electric field, and as soon as light enters into that material medium, the electric field present in the light wave and electric field of that material medium interact each other. That's why significance is given to the electric field A, not magnetic field B. Therefore, electric field is called light vector. That's why we say light electric field as a light vector, because most of the interaction property depends on electric field dominantly. Now we are going to discuss the basic themes, basic points of this chapter, chapter 10, wave optics. So far we have already discussed that electromagnetic wave. It was essential to discuss about that one, because light itself is electromagnetic wave. So we must discuss about basic terms that is essential to discuss about. So here, now we are going to discuss in wave optics, the first terms that help us that to prove that light is a wave is wavefront. In class 9, in class 10, in class 11, we have learned about the wave, mechanical wave. And mechanical wave is always associated with the variation of materialistic property like density, pressure, temperature, etc., or amplitude. But in case of electromagnetic wave, material medium is not periodically changing, but some property, some basic property associated with the wave itself is changing continuously. That is electric field and magnetic field. So here, in order to prove light as a wave, we must learn wave front. As you know that wave trough and crest was essential to discuss about the wave. Similarly here, in place of trough and crest, we take wave front. And in the previous knowledge, while defining mechanical wave, you first of all define the trough and crest. And you know that separation between two successive crests is wavelengths, or two successive trough is wavelengths. Here we will define that separation between two wavefront is wavelengths. And there you have seen that crest travel with a particular speed, and that speed is called wave speed here. Here, wavefront itself will travel with a particular speed, and this will be termed as wave speed. So here, let us check out what is wavefront. Before going to define wavefront, we have to discuss about wavelets. You know well that LET, let is a suffix. When this suffix attached with any root word, it changes the meaning. And let means very small things. That means a small part of wave is called wavelets. Now, a wavelet is a point of disturbance due to propagation of light. You know well that when light passes through the space or in a material medium, then it produces a disturbance, and the point of disturbance where this disturbance has been generated, that point act as a secondary source of light, as if light is coming from that or wave is coming from that disturbance point or disturbing point. Although basic source of light is somewhere else, but when wave passes through a particular place in the space, then at that particular place, this wave produce a disturbance, and then this disturbance appears to be coming from that disturbing point, and that disturbing point is called wavelets. And this wavelet is a secondary source of light. It acts as a secondary source of light. From disturbing point or point of disturbance, if some observer observe this, the observer will visualize that light is coming from that disturbing point, as if basic source of light is there at that disturbing points. Now, a wavefront. Now let us, so far we have learned about the wavelets. Now we have to discuss about wavefront. Wavefront is an imaginary surface. Wavefront is an imaginary surface symmetrically enclosing the disturbing points or source of light or source of wave, on which every wavelet or point of disturbance keeps on vibrating or disturbing on that imaginary surface, and that is called wavefront. So remember here, wavefront is a locus of points, that is wavelets, having the same phase of oscillation. It means that wavefront is an imaginary surface symmetrically enclosing the source of light or wave, and at all the points on this imaginary surface vibrates or oscillates in the same phase. That means every point on the same wavefront or on the same imaginary surface will vibrate or oscillate in the same phase. So each and every point on the same wavefront or on the same imaginary surface will be treated as coherent source. Okay, now let us have let us look at the visual picture of wavefront. You know, will here a line perpendicular to a wavefront is called a ray. Remember, basic property of wavefront is that ray of light must be perpendicular to that imaginary surface. If ray of light is not perpendicular to that surface will not be treated as a wavefront. So let us check out first. Take a single point as a point source or a point charge. Here not point charge, here we say point source of light. A glowing bulb, very small glowing bulb placed at this center, and you will see that a ray of light coming from that glowing bulb will radially outwards. So this is the ray of light. You see ray of light. Now, what is wavefront now? Here, we have already told you that wavefront is an imaginary surface symmetrically enclosing the source of light. So here, source of light is a green point here, and symmetrical surface that can enclose it symmetrically, that would be a concentric sphere. So this is the sphere, this is the sphere, this is a sphere. So as we move away from the source, what happens? The radius of symmetrical sphere go on increasing, indicating that the ray of light emanating from the point source becomes diverges away from each other, indicating that intensity of light or energy of light receiving per unit area will go on decreasing because of area of a sphere go on increasing, because as distance increases, radius increases, so area of a sphere go on increasing. Let us now understand. So each concentric sphere act as a wavefront. And now you see here on each sphere, there is a tiny points in red colors or light red colors here, or pink colors you see here. These tiny points will act as a wavelets, and all the points on the given wavefront will vibrate or oscillate in the same phase. Therefore, all the points on the given wavefront will be treated as a coherent source of light. And this point itself also called secondary source of light or wavelets. Okay? And now this is a spherical wavefront. Wavefront could be of different shape depending on the source of light. If source of light is a point source, then wavefront will be a spherical. And if source of light is a linear or cylindrical, and then it's a spherical, so its wavefront will be cylindrical. Like here, for a tube light, its wavefront will be cylindrical, concentric, not concentric, coaxial cylinder. Now, will the wavefront be plane? Your answer would be yes, it could be, but not really plane wavefront exists. If source of light is infinitely far away from us, then the wavefront is treated almost as a plane wavefront. So like sun is very far away from us, so light coming from the sun to us is a plane wavefront. So wavefront will be treated as plane wavefront. So this is the plane wavefront, you know, here. And every points or dot line on this wavefront act as a wavelet or secondary source of light. Got it? And also you know that ray of light must be perpendicular to wavefront. So here ray of light is perpendicular to wavefront. and separation between two consecutive wavefront is called wavelengths. So separation between this and this plane wavefront is called wavelengths, or similarly, separation between two concentric sphere will be treated as a wavelengths. In the same way as we have discussed there in the separation between two successive crests is called wavelength. So here separation between two successive wavefront is called wavelength. Now, pink dots indicates wavelets. Remember, wavelet means secondary source of light. And blue envelope indicates wavefront, and red line indicates here a ray of light. And you see here that red lines are perpendicular to wavefront everywhere. Here, even here, you see a ray of light is perpendicular to wavefront, and even here, ray of light is perpendicular to the wavefront. And now, let us check out Huygens construction or Huygens principle of secondary wavelets. We will learn about that. Huygens suggested that when light travels from the source, it does so in terms of wavefront. That means light source sends out a series of wavefront in every seconds, and on every wavefront there is a tiny point of disturbance, and that tiny point of disturbance acts as a wavelets. That means every point sends out another disturbance forward, or as every points are in the same phase. Therefore, if you draw a tangent to the disturbance of the every points, then this tangent becomes the new position of wavefront. So you know that here initially this dot line indicates initial position of wavefront. Now this wavefront reached to this place here, this lighter blue, and this lighter blue has a point denoted by red dot. You see red dot act as a wavelets, or even you can say that secondary source of light. And now this source, each dot sends out disturbance forward in the terms of a sphere. Here you see this is the sphere, and again this point also sends out, and in this way every point sends out forward a disturbance. And if you draw a tangent to this a small sphere, then this tangent becomes the new position of new wavefront. So initially this wavefront was here, now final wavefront is here, and similarly again. So this is the spherical wavefront, and you see that ray of light is perpendicular. Ray of light is perpendicular. And this is the case of plane wavefront, because as if source of light is here, and as the same spherical wavefront travel a distance of infinitely large distance, then the same wavefront behaves as a plane wavefront. And here you see that wavelets, red dots on the wavefront indicates wavelets. Now, according to Huygens, each point on the wavefront acts as a fresh source of disturbance of light called secondary source of light. According to Huygens, each point on the wavefront acts as a fresh source of disturbance of light and called secondary source of light, or simply wavelets. Second point is that the new wavefront at any time later is obtained by taking the forward envelope of all the secondary wavelets at that time. In another word, we can say that the new wavefront at any time later is obtained by drawing a tangent. Drawing a tangent in forward direction, enclosing or touching all the secondary wavelets sphere at that time. Now, what happens about the backward wavefront? Backward wavefront is rejected. It means when source of light sends out a disturbance forward, then secondary source or every point of disturbance sends out disturbance in all the three dimensions, but only forward disturbance propagates and backward disturbance is negligible. Why? Because reason behind that one is the amplitude of secondary wavelet is directly proportional to half of 1 plus cos theta. So even you can say that, and if theta changes, so in backward direction, if we take out the amplitude of backward direction, then angle theta becomes 180 degree. So cos 180 degree becomes minus 1. So 1 plus minus 1 equal to 0. That's why amplitude becomes 0 in backward direction. So obviously for the backward wavelets, intensity received in the opposite direction of propagation of wave is 0. Next one is that laws of refraction of light at a plane surface, that is now we have, this is the Huygens principle. 2 points is important. If one is one asks you what do you mean by Huygens principle, then you must say that according to Huygens principle, while light propagating, each point on the wavefront acts as a fresh source of disturbance of light. And second one is that the new wavefront at any time later is obtained by taking the forward envelope of all the secondary wavelets at that time. Yes, just you have to remember. And also new position of wavefront obtained by drawing a tangent. This is the another way to say the second points. And you must discuss about these things. And this is all about Huygens principle. And now come to the point, application of Huygens principle. Huygens principles can prove, if Huygens principle is meaningful, then it must satisfy law of reflection and laws of refraction. So let us first check out whether Huygens principle prove the laws of reflection. Let us check out. Let us check a plane mirror here and a ray of light coming from infinity towards this mirror. Then in terms of wavefront, the ray of light coming from infinity, its wavefront will be plane, and this plane wavefront must be perpendicular to the ray of light. And this plane wavefront will be called incident wavefront, because this plane wavefront AB is perpendicular to this incident ray, therefore this is called incident wavefront. And you know that as this wavefront AB has two parts, so first part of this wavefront AB will strike first, that is part A will strike first this reflecting surface, and part B will strike later, because it has to cover a longer distance here. It will come here. So this, as soon as this part strike this reflecting surface, then this part get rotated in clockwise sense, and B will come this direction and A will come this direction. Okay, so here, this is reflected wavefront. Actually, A has reached to position D and B has reached to position C. So this is called reflected wavefront. And instead of just like in ray optics, we were using the angle of incidence as angle between incident ray and normals. But here, we will measure angle of incidence in terms of angle made by the incident wavefront with the reflecting surface and angle made by the reflecting wavefront with the reflecting surface. So this is angle I is angle of incidence and this is angle R, that is angle of refraction, because reflected wavefront DC makes an angle R with the reflecting surface AC and incident wavefront AB makes an angle I with the reflecting surface AC. Now we have to prove angle of incidence equal to angle of reflection. If you see here, if C is the speed of light and T is the time taken by light to go from B to C. As you know well that part of wavefront AB, incident wavefront AB, A has already striken the surface at point A, but other part of this incident wavefront will strike the surface by traveling a distance BC. So it will strike the surface later. It will have travel a distance BC, and during traveling this distance, time taken by the wavefront, this wavefront, incident wavefront, to travel a distance B to C will take the time T. So, or similarly, after striking the point wavefront, incident wavefront here, it will get bounce back and reach to point D. And it will take the same time because the speed will remain same. So it will take the same time as time taken by B to reach C. Same time will be taken by A to D. Show E to Z through F. So here, now total time taken by the incident ray to come from B, and again you see that this is the point E. So ray of light travel from E to F. So it will take time EF divided by C because distance traveled by speed. And similarly, as same light travel from F to Z, so it will again take Fz upon C. So now using trigonometrical concept, here AF is the distance, hypotenuse. So EF equal to AF sine I divided by C, because EF is the perpendicular and AF is the hypotenuse. So here perpendicular equal to hypotenuse into sine I. And okay, similarly FC sine R divided by C. Now you know that AF plus FC equal to AC. AF plus FC equal to AC. So we can replace AF in terms of AC. So AF equal to AC minus FC equal to AC minus AF. And then taking this like, and we have the result. This one. AB is the incident wavefront, CD is the reflected wavefront, XY is the reflecting surface. Now see here, for a rays of light from different part of the incident wavefront, coming from different part of the incident wavefront, the value of AF are different. You know that. For the ray of light from different part of incident wavefront, the value of AF will be different because if you take the point here, point here, here, distance will be different for this point F. But light from different point of the incident wavefront, should take the same time to reach the corresponding point on the reflected wavefront. And this can only be possible when the term this inside the bracket is 0. So sine I minus sine R is 0. Therefore, sine I equal to sine R. Therefore, I equal to R proved. That is angle of incidence equal to angle of a reflection. And that's all for today. This is laws of reflection. Using Huygens principle, we have proved that law of reflection. And next day, I will discuss using Huygens principle, prove the laws of refraction. That's all for today, and video lecture will be uploaded on the YouTube. You must go there to see. Okay, thank you.